question, please raise your hand. Okay, Nat.
A question for Ethan. So when you mentioned that you condense the planons in all three directions, how do I make sure that that does not condense the fracton as well? Because, like, for example, if I just use the usual transverse field, that'll just condense everything, right?
Yeah. So, so we want to. Are you asking at like a technical level or a conceptual level?
So I guess at least at the lattice, the term you're driving is not the usual, just magnetic field, is it, or is it
right?
else?
No, that's correct. So this is the details of exactly how this works are wrapped up in this sort of generalized gauge theory construction that I didn't really do justice to. Essentially, what happens is that, as you were saying, it's kind of awkward to write down sort of kinetic terms which try to condense bound states of fractons, but don't condense single fractons themselves. And the way you get around this is to write down some sort of extended model which has more degrees of freedom. So you put some, like for example, the fracton dipoles naturally sort of like live on plaquettes of the lattice, right? And so you introduce a different kind of model that has spins on the plaquettes as well. And you do things in such a way that when in this model, and when you tune some coupling in some direction, you reduce to the x-cube model. And when you tune a coupling to the other direction, you condense the things that are living on the plaquettes, which get identified with the dipolar bound states in the x-cube model. So it requires sort of like, because there's no obvious way how to do this explicitly, you have to kind of add some degrees of freedom and stuff. I can tell you about later.
Okay, thanks.
Okay, next question from Men.
Hey, so I have a couple questions for each speaker, I guess. So first, maybe for Ethan. So in the case of condensing linons, maybe I just missed the point. So do you get a trivial phase after condensation?
So if you condense one species of linon, then you get kind of a stack of gauge theories, and if you condense two species, then you get trivial pair linon.
Okay, and is that like only, well, at least in the kind of scenarios you have considered, that's the only way to have a direct transition to a trivial phase? So.
Within the scenarios I described, yeah, the only condensation that I described which produces a boring paramagnet is condensing all species of linons.
I see. Okay. But if you are in this planon condensation scenario, so if you condense all the planons, you get a gauge theory, and then you can condense the gauge charge again.
Sure. Yes.
But that's a two-step condensation, I guess.
Indeed. Yeah.
Okay. Thanks. So now I have a question for Yang. So maybe this is kind of a general question that we know the spatial SPTs can be organized in the real space construction can be organized into a spectral sequence.
Yeah.
And we also know that the internal symmetry SPT is also a spectral sequence, right? They are both a cohomology series.
And spectral sequence precisely are you thinking of in the?
Well, the different spectral sequence, like, I don't know. Yes, I guess I'm thinking about Atiyah-Hirzebruch spectral sequence for the internal symmetry case, and for the spatial symmetry case, that's the equivariant cohomology one that you have in your paper. And the crystal equivalent principle, I think, states that the classification final results agree in both cases. But is there a sense that that there's more correspondence between the two spectral sequences?
Yeah, I think there is. Actually, this is a very good question. Actually, there's a way to, I always meant, you probably know the terminology I'm talking about, but so the in the first part, I was talking about a simpler form of the linear space that allows this rapid calculation. So mathematically, that's known as the resolution of associated with a symmetry group. And there's a way to construct a resolution for space symmetry for space groups that is motivated by that is like constructed from a real space decomposition. Like if you start with a space, like if you start with a two-dimensional or three-dimensional space that has a natural action of a 2D or 3D space group, then you can start from that and build a resolution that basically, if you use that resolution, the I think actually that resolution itself is constructed from a spectral sequence, and I think that spectral sequence will give the ATIA. Sorry, I forget the pronunciation of the second person's name. The AH spectral sequence constructed from a real space construction. I don't know if I have a minute. Maybe I can try to find the paper. There's a mathematical paper describing this resolution, and I think if you use that, you get the correspondence between the two approaches.
See, but this is for the bosonic case, right? Or
I think that also works for fermionic cases. So we are trying to work out some concrete examples, because the resolution as talked about, I mean, it's a full-featured resolution with a contracting homotopy. So you can construct the chain map like to and from the standard construction. So using that resolution or using that set of bases, we can apply the same on-site symmetry fermionic SPT rules to compute the classification. So I think that correspondence even works for fermionic SPT phases.
I'm a bit confused by the framing of the question though, because I mean, as you said, there's not one single spectral sequence for the internal symmetry case. So I don't know which one you expect to be corresponding to the spatial.
Yeah. I guess when I asked,
right. So sorry, I was not. Yeah, I was not. I was thinking about a way to express myself. Yeah, sorry. Maybe I can try to use a whiteboard to do this. Let me try.
it's probably
so
clear in the fermion case where we have already a spectral sequence for the spin cobordism. And of course, if you just if you just replace a group, the internal symmetry group with a spatial one, you should get a spectral sequence on the other side as well.
Right. So what I was trying to say was like, so there's a way to, yeah, we haven't worked out details, but there's a way to, yeah, let me, maybe let me, there's a, so if you start with a space group, sorry, I don't think I'm writing on this. So if you start with a space group SG, what you could do is that you could, so the construction was like you start with you start with some topological space that is basically the three-dimensional space, but you decompose it according to the action of SG, and you have the 3 cells and 2 cells and 1 cells, etc. And the cool point is that the construction tells you that so for each 3 cell, there's some stabilizer group, and you attach to it a resolution of the localizer group, and basically you get a chart like this. I'm not bothered to write down all the symbols, just using circle to represent this, and then you have a special I think you will have some special sequence that if you add those terms together, you get some special sequence such that on the beginning page, I don't remember which page was it, but initially you get some rough ideas like putting the like two-dimensional Fermionic SPD faces on two cells, etc. And start from here, you can try to actually do the special sequence calculation. I guess my point was that I don't know how to express it in mathematical details, but you can also construct the resolution for the symmetry group using a special sequence. And then there's another special sequence for the different layers of Fermionic SPD faces. I think you can switch the orders and do the second part first, and then you get a spectral sequence organized according to the construction of this particular resolution for space group symmetries. But all this is done treating the space group symmetry as an on-site symmetry. So this has no actual meaning of real space construction. And I guess this should match the actual real space construction. So yeah, maybe in this way there's a correspondence.
I see. I'll probably ask you offline for more details.
Yeah.
Yes, I think.
Yeah, I agree. That's probably the best way to do it.
Okay, so yeah.
Yeah.
So the next question.
Let me try to stop this, or maybe, yeah, or maybe Dominic, you can also stop. Oh yeah, I found it. Okay.
Okay, so the next question will be from Shuhen Xiao.
Hi, yeah, I have a question for Ethan. Yeah, thank you for the very nice talk. So in your talk, you describe, you start from the XQ model and you condense various either fractons or lineons to get a different phase. I was curious if you can say a little bit more about the inverse process of that. Namely, can you start with any of the phase you obtain and do something to obtain the XQ model?
Mm-hmm. Yeah, that's a good question. I don't really have a good systematic answer. One of the things I want to know is like, you know, if you there's a question of if you give me a phase, what can I do to it? Some kind of gauge theory, what can I do to it to produce a fracton phase? And there's also like,
right,
even if you give me a critical point, you know, what how do I tell that there's some like deformation of this critical point that produces a fracton phase?
yeah.
So I don't really have.
Yeah, I wasn't thinking about it as some deformation, but like the example I have in mind is in ordinary 2+1D TQFT. We can start with Ising times Ising bar and condense a Z2 anion, and then we get a tori code. But conversely, we can gauge the Z2 E&M exchange symmetry of the Z2 tori code to get back the Ising times Ising bar. So I suppose in any of the phases you obtain, such as the anisotropic model, the stack of 2+1D Z2 gauge theory, the 3+1D Z2 gauge theory, there should be some kind of symmetries or subsystem symmetry that you can presumably gauge to get back to the XQ model.
Yeah, I think you're right. And indeed, all the resulting phases I were talking about all have some kind of like layered structure and stacks of gauge theories in various ways and stuff like this. I haven't thought about like a good systematic way of looking at like, how do I get back to the XQ, or how do I go to some other model or something like this? But probably there's something smart that you can say about that. But yeah, I don't have anything super intelligent to say. But that's a good question.
All right, thank you.
I think the answer is just gauging the rigid one form in Meng's work, right?
But the answer should depend on which phase. It should depend on the phase, right? In like Ethan has various different phases by condensing various kinds of excitations. In each one of them, there should be a symmetry such that if you gauge it, you get back to x cubed. But the symmetry you gauge depends on which phase we are talking about.
Right, but in those phases, don't you have like enough rigid one forms in the other directions to gauge so that you get back?
I'm not sure I have to think.
Say in
But-
3D
but-
toric
but
code,
the
there are
kind of-
3 foliations that you can gauge, right? These rigid one forms.
Well, in one of the phases, it's just the 3+1 DZ2 gauge theory, right? There's no stacks whatsoever, just the ordinary 3+1 DZ2 gauge theory.
But then there are these product of one forms in all the layers.
There's no layer in that phase, right? It's just the 3+1 DZ2 gauge theory.
Yeah, but starting from 3+1 Z to gauge theory, you can gauge some subsystems, some planars.
Yeah, I believe so. Yeah.
You can do it on a lattice model. But
Yeah.
Yeah, actually, also we believe gauging a subgroup of these can give you these hybrid fractal models.
Yeah. I know.
Yeah, it's very similar.
You guys use similar ideas in your paper. Yes. Okay, thank you.
Okay, there was somebody who raised their hand but then lowered it again, so maybe they didn't.
I got my answer. Yeah.
Oh, cool, good. Okay, so if any further questions? Well, maybe I can ask Jan, now that you have this general computational code, are there any, particular problems of practical interest or not of practical interest, but theoretical interest that you hope to solve using this code?
Yeah, I think that's a very good question. So I think I think for people studying SPD phases, one of the problems was that we don't know any like practical realistic examples, like which material would host a non-trivial SPT phase, apart from the ones who are already known, like topological insulators and Condensation chains. So I don't have any realistic models to think about. And I think one of the challenges we are trying to solve is 3-dimensional SPT phases. So for that, there are still some formulas we don't know from on-site symmetry classifications. I think Zheng Cheng and Qingrui are working on them, and we are just waiting for their results to incorporate that into our code. So for now, I think the 2D wallpaper groups are the most complicated ones we can think about, and that computing the classification for them only takes less than 10 minutes. So that certainly was not challenging enough. And for us, because we can't go to 3 dimensions, and it doesn't make sense to, I guess, to compute the classification, 2D classification for 3D symmetry groups. So for now, we don't have any examples in mind to work with. So if you guys have any needs that can use our code, please let me know. So otherwise, so actually the code was has been sitting there for more than a year actually, because we are stuck there, like we were waiting for some results from people working on the on-site classification, symmetry classifications, and we don't have any examples we can think about. So it's just that for now.
What's missing in this formula? I mean, you have abstraction functions, right? Do you mean
like? Right. I heard from Zheng Cheng and Qingrui that in 3D there's a case that they didn't solve in their paper. I can't remember that exactly, but it was stated in their most recent PRX paper. I think that was some case that in 3D you have a H3 abstraction. Like if you started with some Maran chain decoration and you compute the obstruction function for having a for whether you can have a complex fermion declaration. And the thing was that if that obstruction function was not vanishing, that means that obstruction function is not zero everywhere, but it gives you a trivial co-boundary, then they don't have the complete formula for the next H4 obstruction in that case.
I see.
So there's some complicated case that they haven't figured out yet, and we are waiting for that final piece of formula. And there's also another unsolved problem that I didn't mention in my slides. That is, like, once you have different layers, like the classification for Mariana chain declaration, classification for complex fermion declaration, there's a problem of group extension. There's a group extension problem you need to solve after you get each layer from the AH spectral sequence. I heard Qingrui was working on that, but I don't know if he has the full formula yet. So yeah, we're also, like, that part is also left blank in my code. So I'm also waiting for that.
But for example, if the symmetry group is just G times the fermion parity, I saw like that this whole spectral, the spin cobordism is worked out in this paper by John Morgan and sorry, I couldn't remember who else. Is that
right? Yeah, I think that's true. Yes, but yeah, but for us, if we want to deal with space groups that usually contains anti-unitary symmetries, so we probably at least need the case with an anti-unitary symmetry.
I see.
Like that is the I don't remember the name. The spinor, is that the spinor pin cobordism?
Right.
Maybe. Yeah. Do you know if that's worked out too?
Probably not.
Okay.
So we have a question from Don Williamson.
Okay, hey, my question's for Ethan actually. So thanks for the nice talk. I was wondering about these sort of generalized gauge theories you were mentioning. A bit more details. Like, do you know if they're related to the string membrane net models that appeared in some paper by me and Kevin and Dave? Because I found in the past those make it easy to describe certain phase transitions.
Yeah, I think so. Maybe you should talk about this at some point. I think so. So a little bit more detail. It's kind of like what I was telling Nat, right? What you're doing is you want to, okay, if you want to condense some object that or some composite object that naturally lives on some place where you don't already have qubits, then you introduce so then what you do is you introduce new qubits onto the places where the things you want to condense live, and you add some kind of weird and you give the theory with the new qubit some kind of weird weird kind of Gauss's law thing involving the qubits involving the qubits living on the places where the things you want to condense live, and your original thing and your original qubits, and then yeah, that kind of like I think it's kind of I think that it's pretty similar because you're kind of gluing a bunch of various other dimensional things onto the model that you started with, and doing some
You just
kind
do
of
it
various
via
couplings
local
with
unitary, or is it like a
yeah
deformation?
right.
Oh, okay.
Yeah, it's and yeah, sometimes you like stack on some like trivial paramagnets and then mix them in with the other degrees of freedom in some way. And I don't know. It's actually kind of sorry. Yeah.
Yeah. So sorry. Maybe it's just a subset, or maybe just considering the planon condensations, then that it would be the same, and you have some other models that are a bit different as well. It sounds like.
Yeah. I think it's kind of like doing partons on a lattice, sort of. And for condensing planons, it's like this, and for condensing linons or whatever, it's kind of a similar spirit. The things you're trying to condense are not locally creatable, and so you sort of want to add extra spins for them and do various constructions like that. But I think the philosophy is kind of similar.
Great, thanks.
Okay, I wanted to ask another question for Jan, if he's still there. So, so you're talking always about the interaction classification. Of course, the non-interaction classification was also described by generalized cohomology theory, and there's a real space picture that people have talked about. So have you thought about, can you extend your code also to compute non-interaction classifications and maybe also compute the collapse? Like, you say which non-interaction phases are stable to interactions and everything like that.
Yeah, that's a very good suggestion, but yeah, I need to think about it. I guess because honestly, I don't know much about the K theory. I was been trying to learn about it, but yeah, but to be honest, I thought that actually that's certainly from a mathematical point of view, that's certainly much more difficult than the group cohomology theory. So yeah, yeah, I need to think about it. It sounds like a very interesting problem. And I guess I heard there was a mapping from, it was from Alex and Anton Composting, from a mapping between the interacting and free fermion classifications. But it will be a very interesting and challenging problem to try to implement that in computer code. Yeah, thanks for the suggestion.
Yeah, everybody always assumes a non-interacting classification must be simpler because it's non-interacting, but I think the interaction classification really is easier. Anyway, that's my editorializing. So I guess we're pretty much out of time for questions, so maybe I should pass you to the capable hands of the chair for the next session, if you're there.
I think it's me.
Yes.